Hi everyone. I'm Choi from KAIST. Today I'm going to talk about a new type of rootkit called PIkit, a new kernel-independent processor-interconnect rootkit. This is joint work with 6 co-authors from the KAIST. Before discussing about the PIkit, let's talk about a typical root attack scenario. As you know, attacker first needs to obtain one-time root permission by compromising the target machine or by using social engineering. And then attacker installs rootkit by exploiting software or hardware vulnerabilities. And finally, attacker uses payloads together with a rootkit for their malicious activities. So there are different types of rootkits according to the location of payloads and the types of vulnerabilities. So these rootkits are categorized into the following groups. Traditional rootkits are made of only usable codes, and they replace system key binaries. So it is detectable by using integrity checking for those system binaries. And kernel-level rootkits are stealthier than usable rootkits because they exist hardware kernel space, and they modify static or dynamic kernel objects, so it requires code modification or code injection to the kernel. And in this case, this type of rootkits are also detectable by using kernel integrity monitors. And there is another type of rootkit called hardware-supported rootkits. The hardware-supported rootkits are very stealthy because they exist hardware level, and they modify, they exploit hardware features. But previous works on hardware-supported rootkits are also detectable by using kernel integrity monitors because some of our payloads are still located in the kernel space. But our work PIkit is different from all the other rootkits. So what is the PIkit? This figure shows before and after PIkit installation. Like other hardware-supported rootkits, PIkit also exploits vulnerable hardware features. More specifically, PIkit modifies hardware states in Processor-Interconnect in x86 multi-socket server. And the difference from others is PIkit is kernel-independent. That means no code modification or injection to the kernel is required. And malicious payloads for PIkit can be made of only simple read-write memory operations. That means there is no need to invoke system calls. So it is very difficult to detect it by using the existing solutions. So before getting into the detail, let me introduce multi-socket server and processor-interconnect technology. Here is a motherboard of high computing server. As you can see, there are several processor sockets, and local DRAMs are connected to each processor socket. This type of server is referred to as a multi-socket server. In the multi-socket server, the processors need to be connected to each other in order to access remote DRAMs. This can be done by using the processor-interconnect technology. There are 2 examples, AMD Hypertransport and Intel QuickPath interconnect technology. So most of today's data centers and high-performance computing use such multi-socket server. Let's take a look at the processor interconnect in more detail. This is a block diagram of processor interconnect in 4 ways multi-socket server. As you can see, each node contains multiple cores and local DRAMs and a NOS bridge. The NOS bridge contains a memory controller and a router. In the processor interconnect, these nodes are connected to each other by using processor-interconnect technology. So in this case, if certain nodes access remote DRAMs, a NOS bridge creates a packet based on the DRAM mapping information, and the router transmits the packet based on the routing information. So what happens when the nodes access remote DRAMs? If core 1 in node 2 tries to access remote DRAMs, the nodes bridge create the packet based on the DRAM mapping information. We call this DRAM address mapping table. As you can see, this table is located between the core and the node bridge. And the table is initialized by the BIOS at boot time. So in the table, each entry contains a DRAM address mapping range and corresponding each destination node. And these are currently used entries. That means the system is 4-way multi-socket server. And these are reserved for scalability. That means the system can be extended to by 8-way multi-socket server. So in this case, the memory request exists in entry 3. So the nodes bridge create the packet like this. The destination is 3, and the source is 0, and memory type is request, and body contains physical address. So after the router transmits the packet based on the routing table contains nodes and its corresponding output port. So in this case, the destination node is 3, so the packet is routed to the south port. Here, the intuition here is the router only looks at the destination in the packet. So if we are able to change the packet, we can send the packet to wherever we want. As mentioned before, the packet is create the DRAM mapping information. So we are able to, if we are able to modify the DRAM mapping table, we can send the packet to wherever we want. The DRAM address mapping table has several features that helps to modify the DRAM mappings. The first one is configurability. The system needs to be remove or add memories. The table needs to be reconfigurable for providing flexibility. And second feature is extra entries. The system is needed to be designed for scalability. So the number of entries can be equal to or greater than the large systems. And discrepancy. So we can modify the DRAM mappings after it is initialized. And lastly, there is no integrity checking for those mapping informations. So the PIkit exploits these features to modify the DRAM mappings. Okay, let's talk about design and implementation of PIkit. Here is high-level overview of PIkit installation. In the figure, attack node is the node where the mapping table is modified to install the PIkit, and victim node is node where the memories are maliciously accessed by the attacker. So the first thing the attacker have to is to define the attack address region. And then the attacker needs to modify the DRAM mapping table to map this attack address region to victim address region. So after that, any memory request to this attack address region is sent to the victim address region, not an attack node. So the PIkit exists at a hardware level. Existing software room monitors cannot detect it. And in order to define attack address region, the attacker should take care of the following. The allocated attack address region should be only accessed by the attacker. This is for preventing system crashes. And the range of attack address region should follow the resolution of the DRAM mapping table. For example, AMD Opteron processor has 60 megabytes resolution. That means the attacker needs to allocate at least 60 megabytes of physically contiguous memory region. For this, we can use the huge page. In the PIkit, we allocated 1 gigabyte huge page by using a malloc function. And of course, the attacker should keep allocating the attack address region as long as the PIkit is installed. And in order to modify the DRAM mapping table, the attacker first needed to obtain the physical addresses of the allocated attack address region. This can be done by using a phase map file, for example. And actually, the entries are memory mapped registers. In case of AMD, they have 8 sets of DRAM-based limit registers. The DRAM-based register contains base address, and DRAM limit register contains a limit address and its destination node. So this pair of registers can be considered as a single entry in the table. In order to modify the DRAM mapping table, we need to change these registers by using system read-write commands. But modifying the DRAM mapping table should be done carefully. Otherwise, it might cause system crashes. If an attacker is located in node 1 and he allocated the attack address region like this, and he wants to map this region to node 2. In this case, the attacker should create new entry one by one. The first, attacker create new entry that indicates from the original region to right before the attack address region. And then create another entry indicating the attack address region and modify each destination node. And then create another entry indicating the rest of the original region. And lastly, remove the original entry. So after that, any memory request to the attack address region will be sent to somewhere in node 2. So here is an example of PIkit on AMD Opteron server. For example, memory request is made by node 1. The node bridge, then the node bridge create a packet based on the DRAM mapping table, and the router transmit the packet based on the routing table. In this case, the destination node is 1. The packet is routed to the local port. However, attacker allocated the attack address region like this, and he also modified the DRAM mapping table like this. In this case, the same memory request will be found in entry 6, and then the router transmits the packet to each east port, like this. So far, I explained how to implement PIkit on AMD server, but the PIkit can also be extended to Intel architecture. Intel also has DRAM mapping table called source address decoder. And the key difference from the AMD is target address decoder. The target address decoder is an additional table, and it is accessed before the memory request is sent to the memory controller at the destination node. And the TAD contains offset value for remapping discontinuous memory region. So because of this, the TAD offset value can be useful when we want to remap the BTM address region. This is the impact of TAD's offset value. In AMD server, the attack address region is mapped to single BTM address region. But in Intel architecture, by changing the TAD offset value, we can remap the attack address region to different BTM address region like this. So based on the offset values, we can perform a fine-grained attack. So after PIkit is installed, malicious payloads are needed for carrying out the attack. There may be many possible attacks with PIkit. In our paper, we developed 4 different types of attacks. The system corruption attack can be used to crash the system, and bash keyboard buffer attack can be used to snip the user's keystrokes. And bash shell credential object attack can be used for privilege escalation. And shared driver attack can be used for planting hidden backdoor. So we developed the 2 bash attacks on AMD server, and we developed shared library attack on Intel server. I'm going to show you the last 2 attacks. The first attack is bash shell credential object attack. The goal of this attack is overwrite bash's credential data to escalate users' privilege. After PIkit is installed, the attacker runs another shell in the victim node with a normal user privilege. And in order to overwrite the bash's credential data, the attacker first needs to find that credential data in the victim address region. This can be done by using scanning the fingerprinting. As a fingerprint value, we can utilize the credential structure. The attacker already knows his UID and GID, so these consecutive values can be used as a fingerprint value. And the attacker can know the range of kernel's virtual addresses. So the pointers containing these addresses can be used as a fingerprint value as well. And other publicly available values can be used as a fingerprint value as well. So after finding that credential data, the attacker can overwrite the effective UID or UID with 0. 0 means root. So this can be done by using a simple memory write instruction. In the paper, we used non-temporal write non-temporal write instruction to bypass the caching. So this is the result. After overriding the credential data, we were able to get a root shell. As mentioned before, the attack address region is mapped to somewhere in victim node. So there is case where the bash's credential data doesn't exist, the victim address region. It happens quite frequently. But in this case, the attackers can still increase the possibility of finding the credential data by spraying the processor control block. And the second attack is shared library attack. This attack is for Intel architecture. As I mentioned before, when you use TAD's offset value, we can remap the attack address region to different victim address regions. So if target address is fixed, such as shared library, we can perform the more controlled attack. So for the shared library attack, the attacker first needs to obtain the virtual addresses of the shared library. For this, we can write a simple program that dynamically links the libc and run the program and obtain the virtual address of the libc. And then translate to the physical addresses. So after obtaining the physical addresses of the shared library, we can modify the SAD and TAD to install the PIkit. So after PIkit is installed, the attacker can overwrite runtime code in the memory. In the paper, we changed the first 48 bytes of KPWID with simple shellcode. that change the UID and execute another bash shell. Here, even though the library is loaded non-writable memory region, the PIkit bypasses any operating system's page permission checks. So after overriding, if the attacker runs system commands that internally invokes this function and have root permission with that UID, then the attacker can get a root shell. So this can be used as a hidden backdoor. Now I'm going to explain possible solutions. As a possible solutions, you can consider several things. AMD has locked-in features, which is activated by default in your systems. So some of recent systems are not vulnerable to PIkit. But in old BIOS, the option is not a default. So these old systems are still vulnerable to PIkit. And in case of Intel, they don't have any options to lock down the DRAM configurations. And for software solutions, you can consider DRAM mapping monitor. Of course, it should be protected with a secure platform such as Credential or Intel's SGX. And for hardware solutions, Intel might develop locked DRAM feature that AMD has. And in the paper, we also talked about other possible hardware modifications. So please refer to our paper. And as a summary, PIkit is a kernel-independent processor-interconnect rootkit that exploits vulnerable hardware feature in processor-interconnect in x86 multi-circuit server. And PIkit is kernel-independent. That means no code modification or code injection to the kernel is required. In the paper, we developed 4 different types of attacks. And because the malicious payloads of PIkit can be made of only simple read-write memory operations. So we can say that PIkit is very stealthy rootkit. Okay, thank you for listening.
Great, thanks a lot. It's pretty interesting. So again, we have time for questions, if anyone has any questions. Well, I guess I'll start us off. So I'm just curious, when you talk to Intel and AMD about this, what is their reaction? How do they respond to these attacks?
Our response?
It's what? Oh, you did. So you just. But what do they do? My question is, what do they actually do? Yeah.
Okay. So we responsibly disclose this issue to US CERT with a draft version.
Oh, so they. Go ahead.
And we received the response in April 7 from the US CERT. AMD and Intel said to install the PIkit, root permission is required. So they didn't care about it. But as you know, to install the PIkit, install the rootkit, the root permission is always needed. So, and AMD said locked DRAM feature can prevent this attack. But as mentioned before, all the systems are still vulnerable to the PIkit. And until now, AMD didn't mention that these old systems. And we also sent a camera-ready version, but they didn't respond yet.
Great, thanks a lot. So any other questions? Okay, if not, then this is the end of the first session. So let's thank all the speakers.